Unit 7 is going to cover acids and bases, but before we get into acids and bases, we kind of have this pre-unit lecture here on molarity, which is a way to mathematically express the concentration of a solution. It's going to be very important for us to know how to do this when we're talking about acids and bases and how strong they are and what they're going to do and how to do some calculations with them. So we've got to start here with molarity. So what is concentration? We've mentioned this term before, but in case you've forgotten, this is the relative amount of a given substance contained within a solution or in a particular volume of space. Okay. Typically, this is said verbally as like the amount of solute per unit volume of solution. How much stuff you have dissolved in a certain volume of substance. The solute is the substance being dissolved. The solvent is the substance doing the dissolving. So you can think of concentration. There's going to be a mathematical term for us to say how concentrated is this particular thing. Is it really concentrated? Is it really dilute? Is it really dangerous? Is it okay to handle? There's a mathematical way to express that. Okay, it's called molarity. So next couple of terms we need to know here are dilute and concentrated, right? If something is dilute, okay, that means it's got a lot of volume of solvent, but not a lot of solute dissolved in it, okay? And if something is concentrated, you have a very large amount of solute, but not a lot of solvent. Perhaps you've experienced this at some point in your life. If the guy is making let's say the Gatorade cooler out in the football field for that particular day, right? They're putting the Gatorade powder into the container. If they don't put a lot of powder into the container and then fill it up with 10 gallons of water, it's going to be pretty dilute. You're not going to have a lot of flavor, right? The color might not be as vibrant, okay? Now, in the other days, you might have a guy who just puts in, 30 scoops of it and then fills it up, and that is really concentrated, okay? That means you've got a lot of solute dissolved in that same volume of liquid. So you guys are familiar with what dilute and concentrated mean, okay? You just may not have used those terms before specifically. Okay, and you can kind of see, like, over here in this picture, right? I think they've taken, I don't know if this is tea or soda, but here it is really concentrated over on the right side. And what would happen is you just add water to it, it dilutes down, okay, until you get to this point. It's much harder to go well, it's not hard. All you have to do is really just add more whatever it is you're dissolving in there. When you're talking about coffee or tea or soda, it's a little bit more difficult because there's several things involved. But going this way, you're adding more water. Going this way, you'd be adding more solute, okay? Another term we should be aware of is the term saturated. Something is saturated, that means that the solvent cannot dissolve any more solute. All right. So if we take a look at this drawing right here of, say, just a glass that's got some water in it, you may have done this at some point in your life. You take salt or sugar or something like that, okay, and you take the salt or sugar, right, you put it into the water, and it starts to dissolve. You don't see it, right? It dissolves into the water. However, if you add a whole bunch of it, at some point, that water can't dissolve any more of the solute. So what you end up getting is all of it settles out on the bottom there because there's just you put so much of it in there, okay, it can't dissolve anymore. It just settles down at the bottom. So if something is saturated, there's not enough solvent to dissolve that amount of solute. So how do we actually express concentration mathematically? There are several ways to do this, but we are going to use one in particular. Some of the other ones, a very common one is percent by volume. That's where you take the volume of the solute and you divide by the volume of the entire solution. Oftentimes, adult beverages, right, will say ABV on the side of it, which stands for alcohol by volume, okay? And that, whoops, if I can spell volume correctly, alcohol by volume. So that is what percent of the liquid is alcohol. Okay, that's what that is. So it's helpful to know what percent by volume is, but we don't use that in chemistry class. It's not really great for what we need to do, okay, mathematically, but you should know of what that particular thing is, okay, when you're reading it. All right. Some other ones you can do percent by mass, same idea, but instead of the volume of the liquid, you're talking about masses of it instead. Not too common. You might see it every once in a while. There's a unit called molarity, which is moles of solute per kilogram of solution, which is getting close to what we want. However, this kilogram of solution business is it's still kind of a clunky unit to work with. The one that we are going to use, and the term you're going to hear over and over and over again, is molarity or molar, very frequently here moving forward. And that is the moles of solute per liter of solution. Okay. Now, mathematically, the symbol for this, it's kind of a cursive, italicized, capital M, sort of looks like that. And what it is it's moles of whatever you're dissolving, right, the solute, divided by the volume of the entire solution. So what this looks like mathematically, okay, is moles over volume. Now the volume must be in liters. Can't use milliliters. If they give you milliliters, you got to convert to liters. Okay. Another thing you should know about molarity, oftentimes it is indicated by brackets. Okay, so what it's going to look like, say on homework assignments or tests or quizzes, okay, what you'll see is this looks like NaCl, right, sodium chloride, just table salt. If you see brackets around it, that means that whatever's on the other side over here is the concentration of it, usually in molarity. Okay, so if you see what looks like brackets around a particular thing is equal to some number and then the molarity symbol, okay, how you read this verbally is you'd say the concentration of sodium chloride. Okay, that's what the brackets mean around this thing, is equal to, you'd say 1.0 molar is how you would read that. Okay, the concentration of NaCl is equal to 1.0 molar. All right, that's how we read that. So get comfortable with that language. You're going to see that a lot moving forward here. Again, the equation you definitely want to make sure you have down is this thing. Molarity is moles over volume. Okay. Some last information here on molarity before we start doing some sample calculations. Generally speaking, solutions with concentrations greater than 1 molar, 1.0 molar, are considered fairly concentrated, while solutions with concentrations less than 0.01 molar are considered fairly dilute. Now that's, again, generally speaking, because certain things you could have, it could be very concentrated at a smaller number than that, or very dilute at a larger number than 0.01. So again, that's just kind of generally speaking. But if you come across like an acid with a concentration of 1 molar, you should just be careful with it, okay? It's probably more concentrated than what you might find in the grocery store or even Ace Hardware, okay? So remember that when soluble ionic compounds are put into water, they dissociate, they come apart. So really, if you have a concentration of NaCl at 1.0 molar, like the previous slide, what you really have is the concentration of sodium ions is also 1 molar, and the chloride ions is also 1 molar, because it really does come apart, right? We've talked about this. Things that are soluble, ionic compounds that are soluble, when you put them into water, you really get this, okay? Solutes that produce colorful solutions, like the one on the right, this is copper 2 sulfate, can help demonstrate relative strengths, right? 0.1 molar CuSO4 looks like that. 0.3 molar CuSO4 looks like that. 0.5 molar CuSO4 looks like that. So the higher the molarity, the more concentrated something is. Okay, that's what that means. The lower the molarity, the more dilute it is. But remember, not all solutions are colorful. This one's easy to look at because it's blue, and the more blue it is, the more concentrated it is. The reality is, a lot of solutions are colorless, and you can't tell by simply looking at them. So like if you're in lab, you can't just assume something's dilute or concentrated by looking at it. You'd actually need to test it and know. Let's take a look at a couple of sample problems here. So this one says, first one says, a solution contains 1.00 moles of KNO3 in 4.00 liters of water. What is the concentration of KNO3? Okay, so remember our equation for this is molarity is moles over volume. Volume must be in liters, which in this case is good. It already is, so that makes life a little bit easier. Okay, so what we would say here is, right, the concentration of KNO3 is equal to, well, the moles is 1.00 moles divided by 4.00 liters, okay, and to 3 significant figures, right? We're going all the way back to sig figs. We told you we were going to use those all year long. This is 0.250 molar, okay, is how we would say that. So the concentration of KNO3 for that problem would be 0.250 molar. Okay, 3 significant figures. Don't forget this last 0, right? 3 here, 3 here. Answer over here should have 3. Okay. Next question says there are 2.25 liters of a 0.822 molar AlCl3 solution. How many moles of AlCl3 are in the solution? So up here we're going to take this equation, and instead of solving for molarity like we did this time, we're going to solve for moles, right? So we need to get moles by itself. To do that, we're going to multiply both sides by volume. Right, and that's going to cancel out volume on the right. Okay, and we end up with moles inside of a solution are equal to molarity times volume. That's going to be, let's see here, our molarity is 0.822 molar, and our volume was 2.25 liters. Okay, and once again, to three significant figures, 0.822 times 2.25. Okay, we got to round this properly. We get 1.85 moles, right? Since we're solving for moles, we know that's moles. Notice when we write molar here, that really means moles over liters. Okay, right? That's what it means, right? If we look at the equation here. Okay, so it may not necessarily, you might be looking at the units going, how did we wind up with that? Well, really, molarity is moles over volume. So it's replacing writing all of that out every single time. Okay, you should go ahead and try these two, and I'll give you a few seconds to do that, and then I will solve them for you. Okay, so going over these, the first one says there are 0.500 liters of a 0.125 molar NaI solution. How many moles of NaI are there in the solution? So that is very similar to the second problem on the previous slide. So we're going to use that same equation, but again, solve it for moles, which means that moles is molarity times volume. So we just take the molarity given to us, 0.125 times the volume of 0.500 liters, and rounding it to three significant figures, okay, we get 0.0625. Okay. The second one, we haven't seen one solving for this variable yet, but it says, right, a 0.600 molar LiOH solution contains 2.35 moles of LiOH. What is the volume in liters? So now we want volume by itself. So to do that, I'm going to first multiply both sides by volume. Okay, so that cancels volume on the right. Then I get volume times molarity is moles, which is the same equation as right here. And then to get volume by itself, I'm going to divide both sides by molarity, right? Okay, and I get volume equals moles divided by molarity. Alternatively, hopefully you're at a point in your algebra career now where you can look at this and go, okay, well, if V is on the bottom here, V needs to be by itself up here, and molarity, since it's on the top on the left side, needs to be on the bottom on the right side. So that's all we did right there. Hopefully you're quick enough now at this that you can do that without having to think about it. And then it just becomes a simple plug it into your calculator. Number of moles, 2.35 on the top. On the bottom, 0.600 is the molarity. And we get 3.92 liters, again to three significant figures. Now, we're going to start talking about something that we did back in November and December. Molarity calculations. We're going to talk about moles, okay? Because when we are actually making solutions, we need things in moles, but when we are in the real world, we don't have a scale for moles, right? We have scales for grams. And if you recall back in November and December, we were doing work on converting grams to moles, okay? That's coming back. We told you last semester, don't forget it, right? This stuff is going to need to be with you all year long. Stick with it. So here it is, right? When creating solutions that require moles, we must measure the correct mass on a scale and then dissolve it in solution. We don't have a scale that measures moles, right? So we need to measure something in mass, which means we're going to need to use molar mass for a lot of this. So let's take a look at this problem. You need to make 1.50 liters of a 0.500 molar solution of lithium nitrite, LiNO2. What mass of LiNO2 must you weigh out on the scale? Okay, so we're trying to make a very particular solution. So how are we going to do this? Well, the first thing we need to do is figure out how many moles we need, right? You'll first need to solve for moles using the molarity equation. Okay, so that was molarity is moles over volume. And then we need to find mass using the molar mass and moles equation, which you might remember from last semester. Molar mass is grams, right? Mass per mole. Okay. So we're combining a lot of things that have the word mole or sound like mole in them, so trying to keep everything straight is important here. So the first thing we want to do is figure out, well, how many moles are we going to need? And then we can plug that into this equation over here. We also need the molar mass. So actually, before I do anything, I'm going to quickly calculate the molar mass of LiNO2. Okay, and if you've forgotten how to do that, remember, use your periodic table and find the average atomic mass, and then you multiply times however many of them there are in that particular compound. Lithium is 6.94 grams per mole, and there's one of them. Nitrogen is 14.01 grams per mole, okay, and there's one of those. And the last one, oxygen, is 16.00 grams per mole, and there are two of those. So we're going to plug that into the calculator real quickly, and we're going to get 52.95 grams per mole. So we've got that part figured out for when we are using this equation, right? We've got this one figured out. Okay, so let's solve this for moles, right? We need to move V up to this side. Same equation that we've had before, right? As on the previous problems when we were solving for moles. Moles is now molarity times volume. I'm just rearranging that equation for moles. Plugging in our numbers here, the molarity is 0.500 molar, and the volume is 1.50 liters. Okay, to three significant figures, right, that is 0.750 moles of, and we're being particular here, LiNO2. Okay, so now I have the moles and the molar mass in my molar mass equation. I can solve for the grams, right? How much it weighs, right? How much must you weigh out? Well, to get grams by itself, I just move moles up to this side, right? Moles here is going to get multiplied on both sides, so I get grams, okay, or mass, however you want to say it here, grams. There's so many M words, I'm going to try to keep them separated. Moles times molar mass, right? If we want to figure out how much it weighs. So let's take a look here. So we got grams is equal to, the number of moles is 0.75, oops, not a very good 0.750 moles times a molar mass of 52.95 grams per mole, right? Remember, notice our units here cancel out. If you forgot about this, that can also help you remember how to solve it. Okay, is equal to, and we're going to get three significant figures with this answer. We got 0.75 times 52.95. To three significant figures, this is 39.7 grams of LiNO2. Okay, so what that does is that means that, let's say I wanted to make this particular solution. I needed 1.50 liters, and it needed to be 0.500 molar. That means on this scale, okay, I would need to weigh out 39.7 grams of this chemical. And notice this number would change based on what the substance is, because the molar mass would change, right? You have to calculate the molar mass. Okay, go ahead and try this one on your own real quickly, and we'll see how you do. Okay, so we have the same setup as the problem on the previous page. We need the two equations, the one for molarity and the one involving molar mass. This says you need to make 0.425 liters of a 0.375 molar solution of, this is nickel carbonate. What mass must you weigh out on the scale? So the first thing you needed to do was, just like the previous one, find the molar mass of NiCO3. So that's what you see right here, 58.69 plus 12.01 plus 16 times 3, 118.70. And then we need to find the moles based on the molarity equation. So we rearrange for moles, it becomes molarity times volume. 0.375 molar times 0.25 liters to three significant figures, 0.159 moles of NiCO3. And then we plug that number into the equation involving molar mass, and we get molar mass times moles gives us grams, so we're multiplying these things again. 0.159 moles times 118.70 grams per mole to three significant figures, 18.9 grams of NiCO3. So hopefully you did well on that. We're going to have plenty of practice with this. This is going to be an integral skill when it comes to figuring out strengths of acids and bases here very shortly. So we want to start with this before we even start talking about acids and bases individually.